Yeah, college. I missed being there. Like, it's one of those scheduling things. Yeah. I'm not Okay, how you doing? Good? Happy Monday. First full week of school. Actually, I have 3 lectures this week, which is kind of cool. So we're in this massive chapter 6, and chapter 6 has a lot in it. So if there's any chapter I would really focus on your efforts over the next couple of well, the homework's due Sunday night, so you have a whole 6 days to work on it. But this chapter brings in so much foundational chemistry to our knowledge and our chemistry base that I can't emphasize how important this chapter is. One, we're learning to speak the language of chemistry, but more importantly, we're going to deal with the concept of electronegativity, which is by far the driving force of all chemistry, except for nuclear chemistry. So this brings in VSEPR theory, valence shell electroparafluid theory. So it brings in a lot of things that are foundational to our knowledge and understanding of building molecules. And that's what we really want to ultimately get to. How are molecules built, how they interact within the body. Okay? So we left off on Friday talking about really ionic bonding or ionic compounds. So there are 3 types of compounds you need to be comfortable with and how they're formed. We dealt with the elemental forms of the compounds. That's just going to be something like ruthenium or iron or copper or nickel. That's just all they are. They're a metal. All right? There are 7 diatomic elements. There are 7 diatomic elements. There are 7 elements that always are paired up as an element. And phosphorus has some weird ones I'm not going to get into. It likes to have 8, but sulfur likes to have 8, phosphorus likes to have 4. So it's not that hard if you follow along. It makes a 7. How many are there? 7. And it makes a 7. Okay, so it's kind of cool. Starting with nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. See how that makes a 7? Okay? And you might be thinking, but that's only 6. Exactly. The 7th one is hydrogen. Okay? So you just have to memorize hydrogen. It sits out there by itself. But those are always diatomic elements. So nitrogen, oxygen, fluorine, bromine, iodine, and hydrogen are always paired up. So you never see just H unless it's an acid, which we'll get to. So as an element, hydrogen is H2. As an element, nitrogen is N2. As an element, chromium is Cr. Right? As an element, gold is Au. As an element, chlorine is Cl2. All right? So that's basically what that's saying. So we learned really how to speak the language of the periodic table through the elements. Then on Friday, we went through making cations and anions. And we learned that if I take a metal and a non-metal, I end up with an ionic compound. And we went through the exercises producing something like calcium nitride, or sodium oxide, or magnesium chloride. Okay? Those are from a metal and a non-metal. The metal becomes a cation, loses electrons. The anion picks up those electrons, becomes an anion, or negative. Then we moved into the polyatomic anions. Those are going to require some memory, some work for you. And we started with oxygen. We formed hydroxide. And we went to nitrogen. We formed nitrate, nitrite, and the ammonia, which is the only positive or the only cation, polyatomic. Then we moved into carbonate, carbonite, acetate, cyanide. Right? Then we dropped down and we did phosphate, phosphite, hydrogen phosphate, dihydrogen phosphate. Cool, right? And then we went to sulfur, and we said sulfate, hydrogen sulfate, sulfide, hydrogen sulfide. And then we finally ended with the weird ones. The perchlorate, the chlorate, the chloride, and the hypochlorite. Okay? So those were all the polyatomic anions. Those are really the heart and soul of speaking the language of chemistry. So in practice, what this would look like, what it forms when I bring aluminum plus, let's do hydrogen phosphate. Oops. Okay, so what's the formula for aluminum hydrogen phosphate? Well, so I got a little work to do. I need to know what the aluminum looks like. And when I look at the periodic table, I know the aluminum wants to lose 3 electrons, so aluminum becomes Al3+. Okay, I had to memorize the hydrogen phosphate. We'll go back, it's the 8, so 8 is going to be PO4 3-, but hydrogen removes one of the negative charges, so this is going to be HPO4 2-, right? So that's hydrogen phosphate. Okay, because I memorized that. It's in the table, it was in your lecture notes from Friday, and I'm working towards the memory work of that. So now when I do my cross multiplication, right, I'm going to end up with Al2 bracket HPO4 3. And that's the structure for aluminum hydrogen phosphate. Okay? And you'll see these through all throughout both medicine, in practical terms, in the work laboratory, even with field biology majors, you'll work with solutions of phosphoric acid, you'll work with buffer systems, lots of different common compounds that come from the combination of these polyatomic anions with metals. Okay? So let's practice one more for you, just to make sure we're tracking. Let's do calcium. Let's do calcium nitrite. Okay, what's calcium nitrite? What's the structure for calcium nitrite? On Friday, it'll be a work day in here. We're going to do a worksheet on these nomenclature, on putting these topics together. Because again, you don't learn chemistry by watching me do chemistry. You learn chemistry by doing chemistry. Right? I can show you how to do it, but in medicine, my wife used to say in residency and in med school, they used to say you do one, you see one, you do one, you teach one. That's how we learn. See one, do one, teach one. See one, do one, teach one. So you can watch me do them, but until you're able to do it, it really doesn't matter. I have a couple pieces of paper hanging on my wall somewhere that says I can do this stuff. So that doesn't do you any good. You have to engage in it and make sure that it sticks, because it's important to speak that language. Okay, so I had to memorize nitrite. I don't have to memorize calcium. I can just look at the periodic table and I know that it needs to lose 2. So calcium is going to be Ca2+. I did have to memorize nitrite. So I always start with the 8. Nitrate 8 is NO3-. So nitrite is NO2-. So NO2- is nitrite. So calcium nitrite, cross multiplied, is going to be CaNO2, 2. All right? So calcium nitrite. Good. And so the quicker that we put those polyatomic anions to memory, better off we're going to be. All right, any questions on that before we move on? Good? Okay, so we've named 2 different types of compounds. First we've named, we should try one more just because we talked about it. Yeah, let's do one more. Because I really want to make sure that this is solid. Draw the structure. Let's do cupric, or let's do zinc. Yeah, let's do manganese. No, let's do cobalt. Okay, let's do cobalt 3 bicarbonate, or hydrogen carbonate. No, let's do bicarbonate. It's the same thing. Bicarbonate and hydrogen carbonate are the same thing. Bicarbonate is what we used to call it. It's the old way of thinking about it or talking about it. We're starting to phase that out. So you'll see in parentheses in your book, you'll see bis and bi and these types of things, but we're moving kind of away from that. Bicarbonate sticks around. So what's cobalt carbonate look like? Bicarbonate.
bracket HCO3.
Good, 3, perfect. Bam. So carbonate, again, I start with the parent. Carbonate is CO3 2 minus. So bicarbonate loses one of those charges, so it's HCO3 minus. So HCO3 minus is bicarbonate, right? Cobalt 3, so this is going to be CO3 plus. So when I bring those together, it's going to be COHCO3, 3. Okay? Good? Okay. Now, we're switching gears. So listen up. This is an important distinction. If it's a metal and non-metal, it's an ionic compound, we use this nomenclature. But if it's a metal, or excuse me, non-metal, non-metal, so now we're not talking about anything over here. If it's non-metal, non-metal, we change the way we name them. Okay? So we need to speak to 10, in this case in Latin or German, they have similar roots. So let's speak to 10 in chemistry. The way we do this is 1 to 10. Most of them are going to be fairly straightforward. So if I speak from 1 to 10 in chemistry, 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is nona, 8 is octa, 9, whoops, not hepta, not nona, sorry about that, hepta, 9 is nona, 10 is deca. How cool is that? So here's the cool thing about counting from 1 to 10 in chemistry. If you look at this, it's kind of interesting. Hexagon, right, is six-sided. Hepta is 7. Check this out. Octa is 8. So October is the 8th month of the year. Nona is 9. November is what? It's the 9th month of the year. And Deca, December, is the 10th month of the year. Isn't that interesting? And you're thinking, no, it's not. It's 10, 11, and 12. How crazy is that? So historically, what happened?
Romans.
Yeah, good old Romans. 2 narcissists, right? They wanted to be forever remembered, and who were they?
Octavius, which is Augustus.
Augustus, Augustus Caesar and Julius Caesar, right? July and August, they wanted to be crammed right in there. So that bumps out 7, 8, or 7, it should have been 8, 9, 10 to, what is it? 9, 10, or 10, 11, and 12. So anyway, to just realize that kind of happened here. But nonetheless, we still have these prefixes for counting. Now, here's why this is important. This is not metal chemistry. You're not going to see any of the metals in this nomenclature. So if I name something like this, and this is where this comes from, and you'll recognize this. So if I have something like this, we all know it as water. But its technical name is dihydrogen oxide. Okay? Still the #1 molecule that kills people. It's called drowning. All right? If you have something that looks like this, what are we going to call that? Well, this is carbon tetrahydride. We have a common name, it's called methane, but we'll get to that when we get to organic chemistry. If I have something that looks like this, it's going to be diphosphorus pentoxide. This is an interesting one. So this is going to be diphosphorus pentoxide. Now, sometimes, and I'm not a stickler on this, you'll sometimes see this pentaoxide or pentoxide. So the A, there could be an A in there because it is pentaoxide, but because there's those two vowels rolled together, it sounds awkward, so oftentimes we just ignore the A. So it'd be diphosphorus pentoxide. Typically, if it's mono, we don't say mono, all right? Monoxide, or carbon monoxide would be something, might be an exception to that. So if you have carbon monoxide, or just carbon carbon monoxide, right? Versus carbon dioxide. All right, and you can keep going with this. What would this one be called?
Trinitrogen, what he said?
Pentachloride, yeah. In that case, you'll leave the A in there. So this would be trinitrogen. Okay, cool. Here's the important thing. I can tell people going, huh? Notice, none of the atoms up here are metals. That's the key. Non-metal, 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 non-metal. Okay? So if I'm naming non-metals put together, I have to use the prefixes. If I'm using metals and non-metals, I go back to the cations and the anions. And if I'm naming just the elements, it's typically just what the word is or just what the name of the atom is, okay? Or the element is. All right, so let's try one more. Just make sure we're tracking with the counting to 10. What would
Hexphosphate.
not A,
Okay.
not A, just its element.
Okay. All right, so phosphorus.
Hexaphosphorus?
Yeah, hexaphosphorus.
Yes.
Decoxide. Decoxide.
Yeah,
Decoxide.
hexaphosphorus, decaoxide, or decoxide. Again, both of those are acceptable. Okay. Good? Any questions on that? That's a lot of nomenclature. Okay? Yes, sir.
Will other chemistry professors prefer one spelling over the other?
If you go to the stock room, and you actually find these, it's that. They're both acceptable, but again, most are going to lose that double vowel, so it sounds smoother.
And they always end in I, don't they?
Yes, they always end in I. Yep. You got it. Okay, good. Now let's talk about some of these molecules, because this is where it gets kind of fun. Let's use the chemistry that we saw in chapter 4 and begin to build some of these molecules, okay? Because where we're headed is to actually be able to use this in a rational way to know what these molecules look like. So what does something like water actually look like? What does something like carbon dioxide or methane or carbon monoxide, what do they actually look like? How can I build the molecule? Because ultimately where I'm going is I'm going to our very first day of lecture where we began to see those molecules drawn out, where we saw things like morphine and heroin, and I think we did a bunch of them. We did, what's the other one we did? Dopamine. And we began to use the structures to understand what the molecules actually look like in real life. Why do we care about that? Well, we care about that because we either want to modify it or understand how it's reacting within the body. Right? There's pharmacodynamics and there's pharmacokinetics. One deals with what the molecule does to the body, the other deals with what the body does to the molecule. Okay? Because the absolute brilliance of Novocaine isn't removing pain, because you can just cut the nerve and get rid of the pain. The brilliance of it is your body, over time, actually breaks the molecule down and restores the feeling. So one's the pharmacokinetics and one's the pharmacodynamics. All right? So you have to understand both, and we will. We'll begin to look at these molecules and see how they actually behave within the body. So we build on this. What does methane actually look like? What does water actually look like? Well, this is when we go back to the periodic table and we look at our Lewis dot structures. We look at the number of valence electrons these have. So if I look at hydrogen up there, hydrogen, if we remember back to our worksheet, hydrogen has 1 valence electron. Beryllium has 2. Boron has 3. Carbon has 4, 5, 6, and 7, and 8. Okay? So we use those Lewis dot structures, or excuse me, those valence electrons now to construct an actual structure for one of these. So let's take methane and let's say, what is the actual structure for methane? What does methane actually look like? Well, carbon brings in 4 valence electrons. Okay? Hydrogen brings in 1 electron times 4. So that tells me that overall, I need to account for 8 electrons. So I need to account for 4, and 4 is 8. So together, 8 electrons. All right? So when carbon has its 4 electrons, and hydrogen brings in its electron, and hydrogen brings its electron, and hydrogen brings its electron, and hydrogen brings its electron. All right? So that's the actual structure for methane. It actually makes sense. Here's where some of you might have heard of it, if not, that's fine, the octet rule. Okay? There are basically, on this thing up here, there are 4 atoms that always obey the octet rule. Right, so listen up. Carbon, nitrogen, oxygen, and fluorine. Always obey the octet rule. Boron doesn't obey it. They don't obey it. Phosphorus can, but oftentimes doesn't. Sulfur can, but oftentimes doesn't. Chlorine can, but again, oftentimes doesn't. So you might be asking yourself the question, if there are only 4 atoms that don't violate the octet rule, why do we call it the octet rule? Should be the octet exception, shouldn't it? Instead of a rule. And here's why. What are the 3 atoms that organic chemistry deals with? Carbon, nitrogen, and oxygen. So the organic chemist, it matters that carbon, nitrogen, and oxygen never violate the octet rule. So that's why I know down here carbon is perfectly happy with its 2, 4, 6, 8 electrons. Okay? Now, let's contrast that with carbon dioxide. What does the structure of carbon dioxide look like? Can we come up with a good Lewis dot structure for carbon dioxide? Okay, so the way we do this, so for carbon dioxide, I just want to draw it and ask how many valence electrons do each of the atoms bring in? What is the structure of carbon dioxide? All right, carbon brings in 4 electrons. Oxygen brings in 6 electrons times 2, right? Because oxygen sits at 6 on the Lewis dot structure chart. So that's a total of 2 times 6 is 12 plus 4 is 16 electrons. Okay? So the structure for carbon dioxide needs to have 16 electrons, and here's the caveat. Carbon and oxygen always obey the octet rule, so each of those needs to have 8 electrons around it to be happy. So we draw carbon with its 4 electrons. And we draw oxygen. We will usually, there's only one exception where it's an internal atom. So oxygen brings in its 6 electrons. So we look at something like carbon dioxide and we say, do we have all 16 electrons accounted for? And the answer is 2, 4, 6, 8, 10, 12, 14, 16. Yeah, we have them all. But here's the problem. carbon and oxygen always obey the octet rule. This carbon only has 6 electrons around it, it's not happy. This oxygen has 7 electrons around it, it's not happy. And this oxygen also has 7 and it's not happy. So what happens with these molecules, again, carbon is the greatest sharer of any electrons. So oxygen comes in and says, well, why don't we go ahead and bring those down there, and let's go ahead and bring this down here. And so what happens with this is carbon actually still has, carbon brings in its electron and places them here and here. Oxygen brings its here and here and puts its other ones here and here, okay? So what happens with this is we start to have multiple bonds, all right? Whoops, sorry. Okay, so I should have 2, 4, 6, 8, 10, 12, 14, 16. So I have 16 electrons. Oxygen has 2, 4, 6, 8. Carbon has 2, 4, 6, 8. Oxygen has 2, 4, 6, 8. Everyone's happy. Okay? So we abbreviate this with this type of shorthand. So a line or a bond is 2 electrons. All right? Okay? So a bond is 2 electrons. Okay? Any questions on that? Okay. So let's build, let's have you practice one again. You saw me do 2. Let's have you do 1. What is the structure can we predict what hydrogen cyanide looks like? HCN. What is the structure of hydrogen cyanide? Cyanide gas. Get it? Sort of? Okay, so hydrogen doesn't obey the octet rule, so it wants 2 electrons. That's all it has room for. Nitrogen and oxygen always obey the octet rule, so somehow we have to have hydrogen with 2 electrons, nitrogen with 8, and carbon with 8. So here we go. So I bring in 1 electron plus 4 electrons plus 5 electrons. Okay, so hydrogen cyanide has a total of 10 electrons. Okay, so when I construct carbon with its 4, and I bring in hydrogen with its 1, that side of the molecule is pretty happy. Carbon and hydrogen hang out over there. When I bring nitrogen's 5 in, one of them can bring in its electron, but nitrogen has that many. So nitrogen's not super happy. So what it does is it says to carbon, why don't we share this one and this one and this one and this one? So when I do that, I bring in hydrogen and carbon. But here in this case now carbon brings in its 4 like that. Nitrogen brings in its like that and puts 2 out here. Okay? So it should account for still 10 electrons. Still should have 10 electrons. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Nitrogen should have 8 around it if it's happy. 2, 4, 6, 8. Carbon should have 8. 2, 4, 6, 8. It's a happy molecule. So that tells me then that hydrogen cyanide, if I'm going to draw just lines, it's a triple bond there. Okay? So that's hydrogen cyanide.
Is there a limit to how many bonds you can have?
For carbon, again, carbon's always going to have 4, so the most it can have is 4. That's 3, you're almost maxed out. The world champion, you have to ask Dr. Harris's, I believe it's tungsten W right there. I think it can have up to 9 bonds. But for us, really, carbon, nitrogen, oxygen are always going to have just 4.
Okay.
How come nitrogen has 5 bonds?
Nitrogen doesn't. It has 8 electrons.
Okay. Or
Here.
not bonds, I meant electron.
How come it has 5? 1, 2, 3, 4, 5?
Yeah.
Because it's in the 5 row.
Oh, okay, yeah.
Yeah, good.
Yeah.
Right. So there's a 5 above nitrogen, there's a 4 above carbon, 6 above oxygen, etc.
Okay.
Okay. Yes.
So when you put the other 2 electrons in the nitrogen, does it matter if it's like together like
No.
that, or if you put one?
No, it'll, if you have, this is actually called a lone pair of electrons. It actually will look like this. Okay? It's actually called a non-bonding pair of electrons. Yeah. Okay? Other questions? Those are good questions. Okay. All right, why don't you try phosphorus trifluoride, and then we'll move on. What's that? Still waiting? So you're going to get through after temperature. Yeah, this is a little more superficial kind of flyover. It is important, right? It's important to send that down later.
I've already spent way too much.
Wait, what's the style?
It took me a little while.
What's that? You take reagents, right?
Just like.
That's what happened.
Once you understand.
Yeah, don't worry. Right, right. Okay, do we get it? So phosphorus, if I look up on the periodic table, it's under nitrogen, which has 5 valence electrons. So phosphorus has 5. Fluorine has 7 electrons times 3. So 7 times 3 is 21, plus 5 is going to be 26 electrons that I need to account for, right? So phosphorus can obey the octet, doesn't necessarily have to. Let's see if we can make it obey it. If it doesn't have to, we'll change it. So phosphorus is going to bring in its 5. Okay. Fluorine's going to bring in its 3. Or excuse me, its 7. Pretty happy molecule. So fluorine should have, fluorine always has octet, always has 8. Hopefully I have 26 up here. So if I do 8, 16, 24, 25, 26, so yep, we're happy. Fluorine has 2, 4, 6, 8. Fluorine has 2, 4, 6, 8. Fluorine has 2, 4, 6, 8. Phosphorus has 2, 4, 6, 8. It's happy. Okay, so it's a happy molecule. Now you might just be wondering, just for fun, for kicks and grins, what would it look like if we had something that violated the octet? And this is kind of an interesting thing, and I won't hold you down. I just want to show you this. It's kind of interesting. So phosphorus can have 3 halogens on it. That's a real compound, but this is also a real compound. Phosphorus pentafluoride. So phosphorus pentafluoride is a real molecule. Okay? Phosphorus pentafluoride because it's non-metal, non-metal, right? Remember that? Non-metal, non-metal? I use the mono, di, tri, tetra. So this is going to have 5 electrons. Plus 7 electrons times 5. So 7 times 5 is 35, plus 5 is 40 electrons. A lot of electrons. So how do we do this? Well, in this case, phosphorus says, all right, fluorine, bring it. And so fluorine brings in its 7. And that should be 40. And so if I do 8 times 5, that is 40. Fluorine always has 8, 8, 8, 8, 8. Fluorine's happy, but look at phosphorus. Phosphorus has 2, 4, 6, 8, 10. So phosphorus has 10 electrons. Violates the octet rule. Perfectly happy molecule. And here's how it does it. And here's why it does it. When you hop down a row, this phosphorus and this sulfur and this chlorine, they now are on the 3rd energy level. And if you go back and look at your notes, you'll notice that the 3rd energy level has the s orbitals, the p orbitals, and the d orbitals in it. It can use those d orbitals to add to the 8 of the s and the 3 p's. Okay? And that's how it actually does it. That's why you don't see a violation of it here. There are no d orbitals for carbon, nitrogen, and oxygen to put electrons in. The n equals 2 here, n equals 2, only has room for 8 electrons. That's it. When you drop down to n equals 3, you now have a bunch more orbitals there and those d orbitals right next to it. And that's how it actually where it puts those other electrons. So that was free, but that's how this actually works. Okay? Now, going back to constructing good Lewis dot structures for 3 molecules, and we're going to move into what's called valence shell electron pair repulsion theory. Okay, VSEPR. Okay, so we're going to reconstruct methane, ammonia, and water. Okay? So methane, ammonia, and water. So when I draw the 8 electrons, 4 and 4 is 8. We already did this. I get this molecule out. Okay? Question then is, what does that actually look like in real life? And here's the way the theory goes. Valence shell electron pair repulsion theory. Valence shell electron pair repulsion theory. That's a theory. It's a pretty good theory, actually. It has some places where it breaks down. We call that resonance. We won't get into that until organic, but it's a pretty good theory. So valence shell electron pair repulsion theory. The theory goes like this. Electron pairs want to be as far away from one another as possible. Okay? That's it. Very simple. Some of you might have done a little thing with balloons in lab with this, or marshmallows on toothpicks, or you might have played with this in I don't know what Dr. Nagalis is doing in actual lab in this. So we use these models. All right, what's the farthest away 2 electron domains, electron pairs can be from one another? The farthest away that 2 can be is going to be linear or 180 degrees apart. That's it. They're not going to be here at 90, right? They're not going to be at 109. They're going to be 180. That's the farthest away 2 electron domains can be from one another, right? What about when I go to 3? Well, 3, what we call this, by the way, this is called linear. Okay? 3 looks something like this. The farthest away that these electron domains can be from one another is in a trigonal, 1, 2, 3, tri-planar. Okay? Trigonal planar. So we call this trigonal planar. Right? This is called linear. Oh, there it is. This is called, wow, it just disappeared. Spontaneous combustion. This is called linear. This is called trigonal planar. Trigonal 1, 2, 3 planar, right? Now, when we get to 4, we have a couple options. One of the things we could do with 4 is you could almost simulate having a 4th bond like that. But here's the thing, if I did that, that's going to put these at 90 degrees from one another. Is there a better geometry to get them farther away from one another? And the answer is yeah. It's this one. And this is one of the miracles of chemistry. This is called a tetrahedron. Okay? This is what carbon prefers. Carbon wants to go into a tetrahedron. And it's going to blow your mind when we get into organic chemistry and see how powerful this tetrahedron is. Especially when we get into this thing called chirality, handedness in life. Unbelievably beautiful. So this is as far away as you can get 4 electron domains from one another. Now I showed you this in the form of diamond. If each of these green is another carbon and another carbon, it builds the diamond lattice. So it prefers to be in a tetrahedron. And here's why. The bond angle here is 109.5 degrees. Okay? So with methane up here, methane then takes its 4 bonds, and here's the way we simulate this. Methane actually looks like this. It puts 2 of its bonds in the plane of the whiteboard. It brings one of them out at me, and it puts another one away from me into the plane of the board. Okay? And this angle here is 109.5 degrees. And that's called a tetrahedron. Okay, this is a tetrahedron. Okay? So, notice what I'm doing when I simulate its, yes?
What would the degree be between the 3 of them?
Between the other ones?
The 3.
All of them are 109.5.
Okay.
All of them, yes, good question.
Except 2.
What's that?
Is 2 180?
Yes, I'm sorry, yes. 2 is 180, and 3 is 120.
Okay.
Yeah, so 120, okay, so this, right, a circle is 360, so 360 divided by 3 is 120, so it's 120, 120, 120. okay? This one's obviously 180, linear, 180, okay? Just stay right there. And then 109.5. So here's what happens in chemistry. This is going to be a little bit mind-blowing when we get to about chapter 12, chapter 11 or 12. This carbon, this chlorine, and this chlorine in this case, are all in the plane of the whiteboard. You see that? You have one coming out at you, don't you? That's this one right here, the dash, or excuse me, the wedge. And the one coming away from you towards me is the dash, this guy here. So how do we simulate three-dimensionality on a two-dimensional whiteboard? Now, that's the best we can do, dashes and wedges, okay? Now, when I get to ammonia, notice ammonia also has 5, 6, 7, 8 electrons. So ammonia looks like this. Okay? That's the Lewis dot structure for ammonia. Nitrogen has 8, 2, 4, 6, 8, like we saw. Happy? But notice, nitrogen only has 3 bonds, 2 hydrogens. It has a lone pair of bonds. Okay? So here's what happens with ammonia. Ammonia takes the tetrahedron, and one of the hydrogens is missing because it's a lone pair of electrons. So that's what ammonia looks like. Still is a tetrahedron, 1, 2, 3, 4, okay? But notice with ammonia, when I draw the three-dimensional simulation of this, lone pair in the board, hydrogen coming out, hydrogen going back. This angle now is 107 degrees. So what happens, lone pairs take up more room than bonding pairs. So the lone pair up here actually takes those hydrogens and kind of skews them a little bit down, just a little. All right, so it breaks them out of that. And when we get to water, again, if I do my Lewis dot structure for water, I have 6, 7, 8 electrons still. 6, 7, 8. So water looks like this. Lone pair, hydrogen, hydrogen. So oxygen always has 8 electrons, 2, 4, 6, 8. So in this case, if I draw my Lewis dot structure, notice, I'll do blue just to keep it consistent. Lone pair in the plane of the board, lone pair in the plane of the board, hydrogen coming out at me, hydrogen going away from me. Now all of a sudden this bond angle here, well, not that one, the bond angle up here is 104.5, okay? So notice what's happening with this tetrahedron. The perfect tetrahedron is 109.5, that's perfect. So when I have methane, okay, so when I have methane is a tetrahedron that has 109.5, perfect 109.5 on all angles, okay? Because these are all bonding domains that we call, all bonding pairs of electrons. Ammonia has a lone pair up here instead of a 4th hydrogen. So that lone pair spreads out a little bit and it causes this to skew just a little bit. So it drops down to 107. With water, notice the way I've drawn it, I've got the lone pairs in the plane. Now all of a sudden with water, you have 2 big lone pairs up here. And what that does is it causes those two to skew, because again, the bonding pairs takes up more room. So it drops it down to 104.5. All right, so this is really the idea of the whole concept of bonding. So with this, you might have a molecule, something like formaldehyde. So you probably have heard of formaldehyde. Formaldehyde is going to be CH2O, all right? So I have to account for 4, 5, 6, and 6 is 12 electrons. And the way I count for 12 electrons is this. Okay, so there's the structure of formaldehyde from a Lewis dot perspective. Again, 12 electrons, 2, 4, 6, 8, 10, 12 electrons. Everyone's happy. Oxygen has 2, 4, 6, 8. Carbon has 2, 4, 6, 8. Hydrogen has 2 and 2. Happy molecule. But here's the thing. What is the predicted geometry using Vesper for this oxygen? Notice, electron domain, electron domain, electron domain. 3 electron domains. What's the geometry there? Trigonal planar. So it looks like that. Lone pair bond. What's the geometry of this carbon? 3. 1, 2, 3, trigonal planar. So this molecule is planar. Isn't that kind of cool? The theory helps me predict what the molecules look like in the real world, and it actually does a pretty good job. It's fairly accurate in its three-dimensional assessment of where these atoms and electrons are.
Are the electron lone pairs always planar with the, like the element?
With the board,
Yeah.
I just draw it that way because it's hard to draw a lone pair with a dash and a wedge. So I just kind of put the lone pair in the plane. It makes it easier. But you could have it coming out at you. It's just kind of what you make it hard. I guess you could do it this way. Make it harder or something, or dash it or something. But yeah, we could. Now, here's what's going to happen on Wednesday. We're going to complicate this because what happens is not. I'll grab you. Not all atoms share these electrons the same. And that's where chemistry kicks in. The most important fundamental property, the axiom of chemistry, is electronegativity. That's what Wednesday is going to be on. Trust me, Wednesday is a really important, again, foundational principle that we will take Vesper theory and actually understand really what's going on with these molecules. Okay? Good. Great day. All right. Have a great rest of your Monday. I'll see you on Wednesday.